Hello everyone, welcome back. So in the last class we have seen stream cipher. So let me just tell you block cipher in some more detail, and we'll be seeing modes of operation. The block cipher process the plain text in relatively large block of a fixed size, that is called block size. Because that means suppose I'm having a plain text of key bit, I'll be dividing it into some parts, some fixed length block, that is called your that is called block here in our case. Okay, so let me just write simple definition. N bit block cipher is a pair of functions, that is E encryption function, PK goes to C, and D, that is decryption. So you will be taking cipher text, and with key it will give you plain text, where my plain text is n bit string and the cipher text is some m bit string, and key will be, you can say, key bit, where m is greater than equal to n. That means my cipher text is expanding such that for all k in k and for all p in p, what is the condition I'm having? If I try to encrypt p, then it is, if I decrypt with the encrypted p, I should get back my plain text. How do you decrypt? With the same key, I'll get back my plain text. So this is what my block cipher is actually. So ideally each key should define by a distinct ek. For every key there will be a distinct ek function, decryption function. For the block cipher considered here, we'll be taking m equal to n. Later on we'll be always considering m equal to n, and then we'll be giving modes of operation. And if a plain text is shortened than the block size, we use padding to process the plain text, so that the input to the block cipher is of the length n. Padding is just adding some extra fixed values, either 111, either add or something like that. So modes of operation, let us come back to the modes of operation, because if I am able to convert it a block, then you have to apply some mode of operation to encrypt or decrypt. See, block cipher are designed to encrypt plain text blocks of fixed length n, generally a power of 2, such as 8, 16, 32, 64, 128, like that. So many methods have been proposed for using a block cipher to let me write, many method have been proposed for using a block cipher to encrypt long messages. Such a method is referred as mode of operation. Mode of operation. Okay. So the modes of operation are designed to achieve the efficiency, security, mode of operations is designed to achieve efficiency, security, ease of use, and many other functionality, and their trade-off as per the requirement. So we are going to see 5 different type of block cipher here. These are ECB, electronic code book, and then CBC, cipher block chaining, then CFB, that is cipher feedback, OFB, that is the output feedback, and last is counter. We call it a CTR. So these are the 5 different block cipher we'll be seeing one by one. Okay, let us start. First is ECB. Electronic code book. So it is the simplest approach for encrypting the message longer than the block size. It simply divides the plain text X into LN bits. It simply divides the message or the plain text X into LN bits and bit blocks, which we call X1, X2 up to XL. Each of them is of L bit size. And encrypt each of the block independently. Each of the block independently. Okay. Similarly, each of the ciphertext are decrypted independently. Let us see encryption and decryption. So encryption, you will just simply use the key and encrypt the block. I am encrypting each of the blocks. So for all I from 1, 2, 3 up to L. And decryption is just use the key and decrypt each of the block. You'll get the plain text XI. Correct. So if you draw, let us try to draw it for all I equal to 1, 2 up to L. I'll simply just try to draw a diagram. So what I am doing, I am having my plain text block. I am putting it in the encryption with the help of key. It will be encrypted and I'll be getting a ciphertext CI. And this ciphertext, if I want to decrypt, I'll put it in the decryption function, and with the help of key, I'll get back my plain text. This is what the simple your ECB, electronic code book. But there is the problem with ECB. That means it is first thing is it is simplest to implement, so that is a good part. But each block is encrypted independently, which not only allows the parallelized implementation in the hardware. That means none of the block is dependent to each other. So I can parallelized do the encryption of the each of the block. So since all the blocks are encrypted independently, corruption of any of the ciphertext block affect to the that block only. It won't affect to the other block. Whereas in the other cases, it will depend on the other block also. See, ECB mode is not recommended for encrypting long messages or keys are reused for encryption. the keys are, if the keys I am using the if I am using same key for all the block, then this is not recommended, because it will be encrypting same. It is actually deterministic. Suppose I am having k, say a will be encrypted the same value. Suppose it is encrypted with z, some key is used, a is encrypted with z, and like that. So in all the block, this a will be encrypted with the z, correct? So that is a problem actually, which can leak the information whether the same plain text was encrypted or not. Thus this can leak some data pattern actually, because a I have used many times in my blog. That's what they can know this z is. So something like, if you want to see, suppose I'm drawing, I'm having a diagram, and I would like to encrypt it. So this encrypted will be what? It will be again, I'll be having some machines of this diagram, because this lines will be encrypted again with the same thing, and here also this will be encrypted again with the same thing. So I'll be able to see, I'll be able to get the pattern actually. Again, since it is encrypted, but I'll able to see some pattern, because this white part will be encrypted with something which is similar here, and then this lining, this will be encrypted with the same thing, some different color, say pink color or something. Okay, so the next one is CBC. CBC, which is called cipher blockchaining. So in CBC, your encryption is like this. First, with the initialization vector, IV we call it as initialization vector. So with the help of IV, I'll get the C0. Okay, and how will I encrypt? I can encrypt the message CI-1. I am XORing with my plain text XI, and I'll be getting my ciphertext CI. So first I'll be using this initialization vector, and I'll put C0. I'll call that initialization vector as C0. With the help of C0, I'll encrypt. Suppose I want to encrypt X1. So I'll XOR X1 with this C0, and then encrypt that with the key, and I'll get the ciphertext C1. So similarly, C2, for C2 I'll be using the C1 for the encryption. That means I am using the ciphertext for the encrypting also. Correct? I'll be using C1 XOR with X2, and then encrypting with the key, I'll be getting C2. For the decryption, C0 is assigned as initial value, and how will I decrypt? This XI will be given as CI-1 XOR with decryption of CI. It is simple. See, I'm having encryption, so I have to first break this. So I'll be using decryption function. So on the CI. So that's what I have written. I was having CI. If I use decryption function, I'll be remaining with this. But I want my plain text XI, so I have to XOR with CI-1. This is what I had written here. Correct. So if you see graphically what is happening, first I'll be having a IV. So let me call it as C0 as IV I am having, and this let me call it as CI-1. This will be XOR with XI, correct? And everything together, this part will be given to the encryption function with the key, correct? So this will give me the ciphertext CI. This Ci will be used for the further encryption of the x2, x3 like this. C0 will be used for x1, C1 will be used to encrypt x2 and so on. So this is my ciphertext. Once I am having ciphertext for decrypting, again same thing, I'll be having Ci minus 1 here, which is actually in that C0 is our IV. I'll be using my xi dash or whatever I have got by decrypting it. First I will actually decrypt it. See, this Ci is first going to the decryption function. As I told you, first I am decrypting this Ci. I'll be getting something. Say I'll be getting some x dash or some. If I decrypt it, I'll be getting this Ci minus 1 plus XOR with xi. What I'll do, I'll XOR with this. Both the thing I'll XOR. If I XOR both the thing, I'll get back my plain text. If it has not been altered, I'll get back my xi. And yeah, for decryption I'll be using my key. So this is the simple diagram which tells you how this cipher block chaining works. So note that in CBC mode, even one bit change in the initialization vector, it affects all the if it affects the in all the following ciphertext, because if I change one bit of initial vector, then it will change in all C1, C2, C3 and everyone. Okay. So that hides the pattern which was there in the ECB mode. But this gain in the security comes at the cost of efficiency, because I have to get this initialization vector, and then it is actually not efficient than ECB was very efficient. Correct. Okay. So let us see the next one, that is third. This is cipher feedback, CFB. What is CFB? How does the encryption is happening? In the case of encryption, again I will be having C0, which is initialization vector, and then Ci is given by ek of Ci minus 1 XOR with xi. If you see in the previous case, this xy was inside, but here what I am doing, I am just suppose I want to encrypt this x1, so I will first encrypt this C0 with the encryption algorithm, and whatever I am getting, I'll just XOR with x1, then I'll get this C1. Correct. For C2, I'll first encrypt this C1, and whatever I am getting, I'll XOR with x2, I'll get my C2. This is how the encryption cipher feedback. And decryption, again this C0 is from IV, and then this XI, it will be given first. See, I am having this, I want the value of xi, correct? So I have to find this thing and then encrypt. So I'll just ek whatever I was having Ci minus 1, I'll encrypt, I will decrypt, sorry, this should be, yeah, actually yeah, this is the decryption function. I'll be just I'll be XORing this decryption function once again, and I'll get this. See, I want this xi, so I just have to XOR with this part, correct? So it will same ek of Ci minus 1 XOR with Ci. whatever my CY is, if I want this XI, I have to XOR with this thing. This is how your encryption function is. So in the decryption also I'm using this encryption part. Let me just try to draw the graph how we are doing. First I'm having initialization, that is CI minus 1. CI minus 1, I'm putting it in encryption. If you see here, I am encrypting this C0 with the help of key. Whatever I'm getting, I'll XOR with the plain text. This thing is XORed with my plain text XI, correct? And then I'll get my ciphertext CI. I'll be using this ciphertext for the another plain text, correct? Where C0 is our IV, and then this CI is sent to suppose I want to decrypt it, then again I'll be doing the same thing, CI minus 1. I'll be encrypting it with the help of key, and whatever I'm getting, I'll XOR it with my CI. These two things I'll XOR. I'll get back my plaintext XI, correct? Where C0 is IV. So as simple as that. This is your CFB mode. Okay. Next is output feedback. This is called OFB. It's called output feedback. What happens here? Encryption. I'll be first taking O0. What is O0? Actually, it is C0, which has been given by initialization vector, correct? And then how will I find OI? This OI is actually encryption of OI minus 1. Okay, and how is your CI? It is OI XOR with XI. It is actually similar to the previous one. It is closely related to your previous one, because in previous one I was having C0 and then I was encrypting this and XORing with that, correct? Okay, how do you encrypt? Yeah, this is how encryption is happening. Decryption, first O0, which is coming from C0, okay, and then OI, it is encryption of OI minus 1, correct? And how the XI will come? XI will be OI XOR with CI. So if you see the diagram, it is quite similar. I'll be having OI minus 1 here. This is given to the encryption with the key, and whatever I am having, I'll XOR with my plain text XI, and I'll get my ciphertext CI, correct? So in this case, actually I'm not putting my ciphertext, correct? I am just putting OI. So whatever I am getting from this encryption, I am giving it back to this. Whereas if you observe, in the case of cipher feedback, I was sending my ciphertext. After XORing, I was getting this CI. The CI was going there. But here what? This encryption value, the encryption of OI minus 1, this is what I am sending it back to the OI minus 1, correct? So that's why it is called output feedback. I am not putting, that was the previous one was ciphertext related. So whatever ci I am having, what happens again, this part is same. I am having y minus 1. O0 is your initial vector. Here also O0 is IV. What I am doing, I'll be putting it with the encryption scheme with the help of key. This will be encrypted, and whatever I'm having, I'll XOR it with CI. I'll get back my plain text, correct? And this guy will be sent back to this, correct? Where in the case of earlier cases, this encryption, the XOR, the CI was sent back. This is what OFB. Okay, the next one is counter. We denote it as CTR. So counter mode of operation is the stream cipher mode, similar to the OFB mode, with the main difference being in the key stream generation. Since it is the stream cipher, so we need a key stream. So in earlier cases, we were having iterative encryption of the output feedback, correct? So here each key stream is computed independently of any other key stream. So let me just write the encryption. For encryption, we will calculate CTRI, which is actually calculated from CTR plus I. If you add CTR plus I'll be telling how do you get the value of CTR. So CTR plus I will give me CTRI. So once I am having this CTRI, I can get my ciphertext CI just by XORing XI with encryption of CTRI. With the encryption of CTRI. Okay, and decryption. For decryption, this part will be as it is. First calculate CTRI, which is just here CTR plus I, and then what? See, I want my plain text, I have to find this guy and XOR with CI, correct? So XI can be calculated just with CI XOR with encryption of CTRI. Okay, I'll get back my plain text. Now what is this CTRI? Let me just write about it. Sorry, let me just ask what is CTR, because I need this CTR to get the CTRI. So CTR is a binary string of given block size. And what is this CTR plus I? Denotes a length of CTR bit string obtained by regarding CTR as a non-negative integer, adding I to this number, okay, taking the result modulo the result modulo 2 raised to mod of CTR. Okay, and converting this number back to the mod CTR bit string. If you take modulo, this will be converted. Converting converted back into a mod CTR bit string. Okay, so what is happening? See, CTR is a binary string of given block size. So whatever block size is, say block size is n, so CTR is a binary string of block size n. Now what is this CTR plus I? So CTR plus I denotes a mod of CTR bit string, that is the length of CTR bit string obtained by regarding this CTR as a non-negative integer. The CTR whatever we are having, consider it as an integer and add I to this number. If you take add I to the number, then take the modulo 2 raised to mod of CTR, converting this number back to a mod CTR bit string. So if you see the diagram goes like this. First, what I am going to do, I am going to encrypt CTR plus I, or CTR I should have said, with the key whatever I am having. I'll XOR with the plain text XI. I'll get back my ciphertext CI. With the same with the ciphertext, I'll XOR it with again encryption of CTR plus I. Correct? With the help of key, and I'll get back my plain text XI. So as simple as that. And I told you that if a plain text is shortened than the block size, additional data is appended to the plain text. That is, you will be just directly writing 111 all the time. There is actually, see, padding causes ciphertext expansion. So due to additional bit appended, we can use ciphertext stealing also. That is another way which can be applied to ECB and CBC mode. Most of today's block cipher construction use the basic design principle introduced by Shannon. What Shannon has said, that he introduced the concept of product cipher, which is also known as iterated cipher, which he described as cassettes of diffusion and confusion layers, and explained that simple operation. Diffusion and confusion we had already seen. One more thing which we need to know, that is avalanche effect. I think avalanche effect also I had written in the previous lecture. It was that each of the output bits should change with the probability half whenever a single input bit is complicated. That means if you change a single input bit, each of the output bits should be changed. So in the next we will be seeing the two currently used uh, system, that is, first is DES and we will be seeing AES. Thank you so much.